Here's the notes for Chapter 2, Section 1. This is axioms. These are me building up to the axioms to form a field, which we'll get to later. So preface this, I'm going to be doing pretty much all of my examples in the set of real numbers. So I'll just put like a little box up here. A, B, and C are all members of the reals, unless they state otherwise. Alright. So, the first three are the axioms of equality. These should all be from geometry. First off, you have reflective, then you have symmetric, then you have transitive. Reflective states that if you have A equal to A, that's a true statement. The symmetric one states that if A equals B, then B equals A. Makes sense. And transitive is A equals B and B equals C. Then A equals C. All pretty basic. But then after that, you're gonna start hitting things that are gonna be new. And so these axioms are done under binary operations. Which are gonna be addition and multiplication. So the first one that we're gonna cover is closure, which is saying that if you have a real A and you have a real B, then the sum must also be real. And if this is true for the set of numbers, instead of working with reals, you're working with the integers or rationals or whatever, then it's closed under addition. And then closure under multiplication is A times B would be in the reals, or whatever set of numbers you're working with. Then you have the associative, which has to do with how you order your operations, but if you only have the one operation. And so it doesn't matter if you have your A plus B in the parentheses, then your C on the outside. Or if you have your A outside the parentheses and your B and C inside of it, as long as there's plus and plus or like that, then they're equal. And this is also true for multiplication, where these two statements are also equal. Because it doesn't matter where you put the parentheses as long as everything stays in the same order. I'll box these, make them easier to. Then you have identity. So an identity element would be an element that when you have something A and you use your operator on it, you still get you get back itself. And so for addition, we have that it's A plus 0 equals A, and then for multiplication, that's A times 1 equals A. And then we have the inverse, which means A plus something equals your identity from earlier, or A times something equals your identity from earlier. And so what would you have to add to A to get the inverse? You have to add negative A, that, and to multiply A to get the identity 1, get the 1 over A. Now something to note is that if you're considering the natural numbers are closed under addition and multiplication. They are associative, but they do not have an identity. Well, assuming who you ask. But if you say that the natural numbers is the set 1, 2, 3, ... it does not have an additive identity because 0 is not included in the set. And same is true, the naturals don't have a multiplicative inverse since all of the naturals are whole numbers. And something to note for the inverses, excluding the case where a equals 0 because that breaks everything. Because 0 times 1 over 0 is not necessarily where you want your calculations to be going. But if you have a set number that fits all these requirements, which the real numbers do, they're closed, they are associative, they have an identity element, and they have inverse elements, then you call that a group. Yay. Alright. And then there's things that you can go on that are slightly more specific than having a group. I'll just erase all this stuff. So let's say you have a group and it's cumulative, which is the same as saying a plus b equals b plus a, or ab equals ba. If it fits these requirements as well, then it's not just a group, then it's a abelian group. And lastly, if you can distribute over your binary operations, so you have your left distribution over, or you have your right distribution. These are the same thing because we acknowledge the cumulative property if you have the distributive property. Or no, if you have an abelian group, and you're working with the distributive property, then you have the commutative property. So you can, if you're working with an abelian group, so you know that these two statements are equal, then you can say abelian and this, that would be a field. And so field is where the binary operations hold closure, associativity, identity, an inverse element. They are cumulative and they are distributive over each other. I think that's it for this unit or section. Bye.